Thank you all so much. Space is freaking awesome. That's our motto at the Adler Planetarium. So I'm delighted to be here today. Those of you who were at my workshop yesterday, I discussed a little bit about my personal life as a scientist in the public sphere, and also one who does a lot of outreach among religious congregations, and also is involved in the higher level academic dialogue between science and theology. And on that note, today's talk is actually in conjunction with a book that's being advertised outside, Interactive World, Interactive God, The Basic Reality of Creative Interaction. You can talk to John or Carol Albright about that book. We're really excited about it. We're especially excited about it for seminary students, but also for anyone who's looking to sort of think about what we're learning through science, what that's telling us about nature, and how that might influence the way we think about God today and God's action in the world. So it contains essays by scientists, physical scientists, biological scientists, reflections by theologians, and I'm really proud of what Carol and John and Milad, the editors, put together. So check it out. So what I'm going to be talking a little bit about today is I'm giving you a brief outline. I apologize, I am going to be looking back. I'm very used to running things from my laptop and seeing my notes page, so instead I'm going to be looking back a lot, but no worries, I'm paying attention to you guys too. So a little bit about the nature of science, not very much. We can't talk about all of cosmology in an hour, so I'm going to take you on kind of a whirlwind tour of the universe, the scale, some of the contents of the universe. First of all, let me say astronomy is an incredibly multidisciplinary science. These days it embraces astrophysics, astrochemistry, astrobiology, which is the study of the origin, distribution, and future of life in the universe, planetary science, geology, cosmology, the study of the large-scale evolution of the universe, the beginning and the large scale. So astronomy is what we kind of use as an umbrella term for all of these disciplines. So the latter part of my talk will be about this idea that what we're learning about the world is telling us that nature looks like it can be characterized more as a web of relationships than a collection of things. And I'm going to give you examples both from how we understand some scientific processes that are important in astronomy, and also how this is the way science itself progresses these days. I think it's sad that a lot of kids in school learn about a few scientists from history. You know the ones I'm talking about, Newton, Einstein, Darwin, and they come away with the thinking that our whole scientific background or our whole scientific understanding rests on the backs of, if you'll forgive me, a few dead white guys. Thank you. I see you took that in the spirit in which it was delivered, when in fact science these days is very much a community endeavor. So, and then I'll be giving a few of my own reflections on this, and understand I'm not academically trained in philosophy or theology. My background is physics and astronomy, so forgive me if I come across as being very naive to most of the folks in the audience. Great movie. How many people have seen The Martian? Show of hands, some of you have. This is my favorite quote, and almost all my scientific colleagues agree on this, where Matt Damon says, I'm going to have to science the expletive out of this. And you know why we like this quote? Because it turns science into a verb. And that's really what science is all about. Science is a process. It's not a dusty collection of facts. It's a process by which we increase our understanding of things. Now, science is a remarkable tool, of course, for problem solving. But today, it's also been an incredibly successful instrument for probing the nature, origin, and evolution of the cosmos. Now, some of you may be familiar with this gentleman here, John Polkinghorne, who's coined this impressive phrase, epistemology models ontology, retired Anglican priest and physicist. Most scientists don't know these words. It has been said that philosophy of science is to scientists what ornithology is to birds. So, and the mark that doesn't hit too far from the mark here. Now, in the Small Catechism, we have Martin Luther asking, what does this mean? Well, of course, the definitions of epistemology and ontology were up there. They're gone, but it's okay. In the context of science and scientists, we scientists are critical realists. That is, we believe that what we learn through science really gives us some insights into what truly is. That is, we don't think those dinosaur bones buried in the earth were put there by God to deceive us. Another great movie, WALL-E, a great movie. Classification is the beginning of science. I love the scene from, you remember the scene from the movie WALL-E? Okay, I'm sure a lot of you have families. You've seen WALL-E, right? Okay, well, there's this great scene where WALL-E is trying to figure out what to do with the spork. Is it a fork? Is it a spoon? Eventually, he lies it down between these two. This illustrates a problem with classifying things. Classification is where science begins, not where it ends. This is something you all did probably when you entered kindergarten. You were given a series of objects and asked to sort them by what's the same and what's different. The problem here, of course, is how you sort things depends upon the properties that you consider to be the most important. Is it color? Is it shape? What is it? What we're learning in astronomy today is that we're living in a universe of continua, where something isn't just this or that, but it can be a combination of both. I like to say we live in a non-binary universe. This is where science starts, it's not where science ends. Let's look at an example of this. Pluto. Why isn't Pluto classified as a planet? Everybody's favorite question. We were amazed when the International Astronomical Union in 2006 reclassified Pluto from planet to a category called dwarf planet. The outcry was enormous. People were horrified. How could we have demoted Pluto? How could we have killed Pluto? We love Pluto. Pluto is a very interesting and unique world. It might surprise some people to know that until 2006, we didn't have a universally agreed upon definition of a planet. The word planete derives from Greek, from ancient Greek, and it basically means wanderer. The planets to the ancient Greeks were those little dots of light in the sky that move differently from the so-called fixed stars. Okay, they weren't worlds. Today, we call worlds by many different categories. And the point of the IAU reclassification, what we consider a planet now is based on 3 criteria. Does it orbit the sun? Check. Got to make sure this is doing what I want it to be doing. Pluto orbits the sun. Pluto is also large enough, it's massive enough for gravity to pull it, its self-gravity to pull it into a more or less roundish shape. So check. Whoops. Not what I intended. Where Pluto fails is that Pluto has not cleared its orbit. We've discovered in recent years that Pluto is one of many icy bodies out in what's now known as the Kuiper Belt. Some of those objects are pretty similar to Pluto. They're also large worlds. So now we have this word salad group of terms: dwarf planets, planets, asteroids, comets. These are all different kinds of worlds that orbit our sun. So I'm going to take you on a quick tour. Oh, before I get there, the important point here is not what we call Pluto. This classification may change 20 years from now. Scientists are still debating how we should classify Pluto. But to get too caught up on what we call Pluto is to miss the point. What's important here is this process gets us thinking about how is Pluto related to the other worlds of the solar system? What can these relationships tell us about the architecture of our solar system and also about the origins and evolution of our solar system? So it's all about relationships. It's not about what we actually call Pluto. So we're going to go on a little whirlwind series of scales. I'm going to be showing you some cylinders, cylindrical volumes with diameters written above there. Hopefully you can read that. So starting with looking at the blue marble, the famous blue marble view of Earth, you're looking here at a diameter across this view here of about 15,000 miles. If we go out to the solar system, out to the Kuiper belt and a little bit beyond, we're looking at a distance of about 10 billion miles. Now I know some of these, you can't see the text in some of these. Don't worry, we're going to get to much neater slides in a while. The point I wanted to make here is that the Sun and the Earth are very close to each other on this particular diagram. They're 93 million miles apart, but it still takes light 8 minutes to travel the distance from the Sun to the Earth. I want you to think about that as we go to larger and larger scales, and I want you to think about this. We never see the universe as it is at this instant of time. We're always looking into the past. Your eyes, in a sense, are time machines. We're always looking into the past as we look to further and further distances. As far as we know, nothing travels faster than the speed of light. Information doesn't travel faster than the speed of light. If we have a giant solar flare right this second on the Sun, we don't know about it for at least 8 minutes. Going to what we call, is this advancing twice? I can't see every time I hit it. Okay, my bad. So going to one step further out, the solar interstellar neighborhood. Now we're looking at about 30 light years, and these are not all the stars. They're some of the brighter stars in the solar neighborhood. I want to tell you a little bit about the diversity of stars. Stars come in an amazing range of sizes and brightnesses. The brightest blue stars in the sky, intrinsically, those stars are 10,000 times brighter than our Sun. There are also dinky little red dwarf stars that are intrinsically 10 or 100,000 times dimmer than our Sun. 50 of the nearest 70 stars are these dim little red dwarfs. Red dwarfs are really long-lived stars. Stars are basically giant nuclear furnaces that fuse lighter to heavier elements at their cores. Those massive blue stars that are 10,000 times brighter than our Sun, they're the gas guzzlers of the universe. They go through fusing heavier and heavier elements and explode after they're only a few million years old. Red dwarf stars can do their fusion process peacefully for trillions of years. And our best estimate of the age of the universe is 13.8 billion years. That means that any red dwarfs that were formed since the start of the universe, they're still around. So they're of particular interest in the search for potentially habitable planets orbiting these stars and possibly life. So going out a little bit further, more than a little bit further, the diameter of our galaxy is about 100,000 light years. It takes light that long to cross from one side to the other. The left side shows you the beautiful insider's view, and I hope you've all seen the Milky Way at one point in your lives. It's a sad fact, unfortunately, that by the middle of the 21st century, very few people on the face of this planet will ever see the Milky Way in the night sky, and that's a crying shame. This beautiful view that people might have had thousands of years ago will be gone. On the right side is the shape of our galaxy as we've been able to infer it making measurements from our place orbiting the Sun in the galaxy, about halfway out from the center of our galaxy. We never see our galaxy from the outside, of course, because we would have to travel over 600 quadrillion miles to travel the distance of our galaxy. Going out to larger scales, galaxies are arranged in groups, and the two largest galaxies in our local group are the Milky Way galaxy and the Andromeda galaxy. These galaxies are actually approaching each other, and it's predicted that in several billion years' time, they'll merge. And notice I say merge, not collide. That's because sizes of individual stars, millions of miles, the distances between average stars, tens of trillions of miles. So galaxy collisions are shaped by the gravity between the stars, but the actual stars don't collide. So now we're looking at a diameter of space about 6 million light years across. On even larger scales, galaxies are arranged in these superclusters, where there are beautiful filamentary structures of galaxies that we see as we look out in various directions from the Earth. And on the very largest scale here, this is kind of boring image here, and it's meant to be. We're not looking at any kind of structure here. This is to illustrate that we actually have a horizon in our universe, beyond which we cannot see for various different reasons. Now, you might notice, those of you might be saying, well, you're looking at a diameter 93 billion light years across. How can that possibly be if the universe is only 13.8 billion years old? And the answer lies in what we've learned in the past 6 decades or so, well, more than 6 decades, that our universe is actually expanding in time. And when I say a galaxy is 10 billion light years away, what I really mean is the light from that galaxy left that galaxy 10 billion years ago when the universe was a lot younger and a lot smaller. So we actually have another horizon that we can't see past, and that's what we call the microwave background radiation, which is when the universe was so hot and dense that light and matter were intimately connected. I'll say more about that in a little bit. So now I want to talk a little bit about how our scientific understandings have influenced theology, at least since the 17th century. Science and philosophy has kind of always played a role in theological thinking. But in the 17th and 18th century, I think it played a particularly detrimental view. Newton envisioned space kind of like a passive stage, where the things in the universe were related by forces. The material world behaves in terms of simple cause and effect. Gravity is thought of mathematically as forces between two different masses. And unfortunately, this led to a very mechanistic view of nature. The universe is like one big mechanism. What does that turn, whoops, wrong way. What does that turn our thinking about God to? Well, it kind of makes God into some big kind of cosmic engineer that's built this mechanism, which occasionally has flaws. So God comes in to tinker and, and correct this process, the flaws. And this led to what we call God of the gaps thinking, where either science has explained it, it's got a material cause, or God did it directly. God as explanation, the capital E, is put into competition with scientific explanations, and God becomes yet another cause competing with physical causes. And in this kind of a picture, in this kind of way of thinking about things, as our knowledge grows, as we learn more and more about how the universe works, God's role becomes smaller and smaller. And kind of the epitome of this is expressed in deism, a view that God sort of started things out and then stepped back, hands off. This view was very prevalent at the time of the founding of our country. Many of you may know that a lot of our founding fathers actually weren't theists, but were deists. And this really influenced the way we thought about God. And, you can ask the question, this doesn't sound very much like the God of all that is, that we affirm in the Nicene Creed. Our thinking about these things has changed a lot. So now we're going to pass into the part of my talk where I talk about the interactive, what we have learned about our universe that's indicating that it's not simple cause and effect, but it's all about interactions where you can't separate one thing from another because they're intricately entwined. So let me start out with light and matter. And oh, geez. Okay, so I'm going to start out on this. So that I'm not just talking about Newton, Einstein, and Darwin. Here are some very important scientists from the past that you may not have heard of. Father Angelo Sekhti, the father of astrophysics. Nice double entendre there because he was a Jesuit astronomer. And he's kind of responsible for turning astronomy into astrophysics. Prior to the 19th century, astronomy was mostly about how things move in space, how worlds interact through gravity. Angelo Sekhti was one of the people who helped turn astronomy into a study of what are those celestial bodies actually made of. He built a spectroscope, and a spectroscope being a device that spreads light out into its component colors. And he looked at different stars, and he noted different patterns in the spectra from these stars, the patterns being those dark lines that make these things look like celestial barcodes. Now, at the time, he didn't have the physics to understand why, but he did know that these patterns were related to the elemental composition of these stars. And he has this beautiful, I guess maybe it's in the next slide here. He talks about this and how the study of spectroscopy was so important to determining the composition of stars. Cecilia Payne-Gaposchkin, her dissertation in the early 20th century is actually pretty widely considered to be one of the most brilliant, if not the most brilliant, dissertation in astronomy in the 20th century. She took some of these ideas a step further, related these patterns not just to composition but to temperature, and she was basically the person who figured out that the most abundant element in the universe is hydrogen, and that's what the stars are made of. So two people very, very important in the history of astrophysics. Now, those of you who were at my workshop yesterday heard me talk about clergy days at the Adler Planetarium, where we have free days for clergy and we celebrate clergy contributions to science. We put posters around the planetarium in various places, and of course, Father Sekhti is among our poster clergy. So let's talk a little bit about how we think of gravity and matter these days. Before I start here, I want to say that Einstein did not overthrow Newton. Newton's laws of motion, Newton's equations that describe the way gravity work perfectly well in most circumstances. I like to tell people, if you're driving down the highway and you're tailgating somebody who's driving 70 miles per hour and you're like 2 feet behind them, you don't need Einstein to tell you what's going to happen when the car in front of you slams on the brake. But the thing is, our mathematical descriptions of the world are very large, and on very, very small levels, our mathematical descriptions have to change because the world behaves sort of strangely when you're talking about massive objects with a lot of gravity, or when you're talking about the behavior of atoms. So our mathematical descriptions need modification. Einstein envisioned gravity and matter, gravity and matter a bit differently. So we go from talking about space as an empty stage to space and time sort of being intricately combined into this fabric that's no longer a static backdrop, but it's flexible. It can twist, it can bend, and gravity is in the nature of space-time. As John Archibald Wheeler has said, space-time tells matter how to move, and matter tells space-time how to curve. You can see this graphic here about the Earth orbiting the Sun, and the gravitational field around the Sun being sort of depicted by this gravity well. And so it's dynamic, it's interactive, and matter and space-time really can't be considered independent one of the other. Now, if you don't particularly like or relate to that graphic there, maybe you'll like this one. Okay? Now, I'm looking for the expressions of the people who have cats, because if you have cats, you know what I'm talking about here, okay? Every night, I can tell you my cat messes up my space-time continuum. And by the way, I don't spend a huge amount of time on the I Can Has Cheeseburger site. So one of the predictions of general relativity, sketched out in 1915, has been probably the most successful theory of physics. There's a whole long list of predictions. We can't talk about all of them. Every single one of them has been experimentally verified at this point in time. The last one, in 2015, 100 years after the formulation of general relativity, and it's because it took us that long to develop the technology to detect something you may have heard of, gravitational waves. I'll be talking a little bit more about that in a minute. But this is one of the predictions of general relativity, that this fabric we call space-time should be expanding, so that the distance between galaxies in time actually grows. Now, observationally, the astronomer Edwin Hubble is credited with the discovery of this expansion, which predicts that galaxies further away from us are going to be traveling at greater speed from us. You think of it like blowing up a balloon, put a bunch of dots on that balloon, and any one dot is going to see the dots further away, moving away, expanding away faster. So this is one way to visualize that expansion. Now, interestingly, boy, I'm not getting the hang of this, am I? Interestingly, a Belgian priest named Georges Lemaitre discovered this Hubble relation 2 years before Hubble did. And he wrote an article in a rather obscure Belgian journal. And 2 years after Hubble's law was published, Lemaitre, his paper was translated into English, and the equations that describe this expansion had been removed. They were removed by Lemaitre himself because he thought his observations were not good enough to validate the discovery. He didn't think he deserved credit for the discovery. So there's a nice picture of Lemaitre with Einstein in 1933. And by the way, think about this. There's a lot of irony here, right? How many times do you hear today people referring to the Big Bang as atheistic? The idea of the Big Bang was proposed first by Lemaitre, who extrapolated back, saying, well, if space-time is expanding, there must have been a time in the past when everything was together, and the universe must have had a beginning. So he caught a lot of flack, too, from the scientific community, because a lot of scientists wanted the universe to be in a steady state, wanted the universe to have been there forever, not to have had a beginning. And he was accused from both ends of the spectrum. Now, I want to let you know, this is an important point here, that the Big Bang is not like an explosion that sends shrapnel into space. What this is all about is that space and time, as we know it, as we currently measure them mathematically, had their origins in the Big Bang. So it's the expansion of space, not some primordial explosion that spit galaxies out across the universe. Lemaitre's response to the suggestion that his deeply held religious beliefs led him to this view, and I have to read this because I don't have it memorized, so you'll forgive me. As far as I can see, such a theory remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. For the believer, it removes any attempt at familiarity with God. It is consonant with Isaiah speaking of the hidden God, hidden even in the beginning of the universe. Kind of like the ultimate nail in the coffin for God of the Gaps thinking. God is the source of everything, but we don't find God through science. Another prediction of general relativity, gravitational lensing, this incredibly beautiful image of a cluster of galaxies. Those streaks, those arcs that you see in the background, those aren't instrumental artifacts. That's what happens to light as it passes through a strong gravitational field. A colleague of mine, a former friend, well, not a former friend, but she's no longer at the Adler Planetarium, wrote a book called Einstein's Telescope, and how some of these ideas relate to a few of the new things we've discovered in the universe called dark matter and dark energy that you may have heard of. We'll talk briefly about that in a minute. But you'll notice all of these streaks. Here's a diagram that kind of helps indicate what's going on there. So these clusters of galaxies are very, very massive, and they act sort of like lenses in focusing the light from background objects. So you get distorted, you get double images, you get arcs, depending upon the geometry, you get all sorts of multiple images just from the gravity. And what's neat about this is the amount of distortion you get actually gives you a count of the amount of matter that is needed for the gravity to distort like that. This is one of the ways that dark matter was discovered, because the amount of lit matter doesn't add up to have enough gravity to actually cause the way the way you see the distortions in gravitational lensing. So a little bit about dark matter and dark energy. What are they? Would it surprise anybody to know that we don't know what about 95% of the universe is? And that's just the so-called known unknowns. Dark matter and dark energy right now, we don't know what they are, but if you assume that they exist, they explain a lot of attributes of our universe. Two people here, Fritz Zwicky and Vera oh my goodness, there are some people that have mysteriously disappeared from and I don't know why. Sorry about that. Fritz Zwicky on the right there were three gentlemen who a few years ago won the Nobel Prize in Physics for having discovered dark energy, having made the discovery that far from slowing down the expansion of the universe, you expect, if gravity is the only dominant force at large distances, that matter would cause the expansion to slow down. It's not. It's speeding up in time. And we know that from finding distances to these supernova explosions in the distant universe. Supernova in astronomy are what we call standard candles. You can calibrate their absolute brightness to their apparent brightness, so they're very, very useful in figuring out distances. And these things are what I like to call known unknowns. We know about them through their interactions with things we know about. Of course, it raises the question, and I believe Ron was posing something like this earlier, what unknown unknowns might be out there? What are we missing that we don't know anything about? Gravitational waves, okay? 2015, the first signal of two black holes merging in the distant universe was detected. Black holes are incredibly massive, dense objects. It was predicted in the general theory of relativity. Einstein predicted their existence. These are actually ripples in the fabric of space-time due to the motions of very massive objects. And when I say ripples in the fabric of space-time, doesn't this sound like science fiction? It's not science fiction anymore. These were actually detected by an instrument known as LIGO, the Laser Interferometer Gravitational Wave Observatory, and not just one detection, but they've since come out with announcements of subsequent detections. Let me tell you how difficult these things are to detect. Einstein knew that he predicted these, but he didn't think we'd have the technology to actually be able to detect them. These waves, as they pass the Earth and were detected, they essentially are like the Earth being compressed and expanded by the width of an atomic nucleus. That's how minuscule. This is greatly exaggerated as these waves pass. Yeah, yeah, it's a good thing, right? I mean, some of you are thinking, well, we haven't started drinking yet, right? Why is that going back and forth? Again, a visualization to make obvious what's going on, something that is such a minor effect, way outside of the realm of ordinary human experience, which is the realms that we're in scientific discovery these days. So actually, let me go back a minute here. I'm going to talk about something now near and dear to my heart, if I can go back a minute here. So I study how stars and planets form. I use infrared and radio telescopes to probe cold clouds where we now understand clouds collapse through gravity and form stars and planets. This idea goes back over 200 years. Was proposed as a hypothesis by Immanuel Kant and Pierre Laplace to explain some of the features of our solar system. Namely, it's flat, the planets all orbit in the same orientation, and gravity pulls things together. There was an understanding of orbits, thanks to Sir Isaac Newton, back in the 1700s. And the picture on the left here sort of shows how this works. You start with a slightly spinning cloud of gas pulled together by gravity. It flattens out. The sun builds up in the center, or a star, maybe, builds up in the center, and then planets can form in this extended disk. It's a nice, orderly process. Well, like so many other things, in astronomy is what we call a very theory-driven science. What I mean by that is there are a lot of things that were predicted well before we had the technology to observe. And of course, we can't just run time backwards and observe our solar system being formed. But what we can do is look out into space and locate regions where these processes are actually going on today. So Orion, beautiful winter constellation, the Orion Nebula, a lot of people are familiar with it. Your small backyard telescope won't give you the Hubble Space Telescope view. Oh, jeez. What you're looking at here is a cloud of hot gas about 1,500 light years away. The diameter of this field is only a few light years, so think the distance between the sun and the next nearest star. And by the way, what I didn't mention when I showed you the local interstellar neighborhood, our next nearest star is a little over 4 light years away. It's called Proxima Centauri. It's one of 3 stars in the Alpha Centauri system. In recent years, like within the past couple of years, we have discovered more or less an Earth-sized planet orbiting in the so-called habitable zone around this star, the nearest star to our sun. Has a world that is orbiting its star at the right distance, perhaps to have liquid water, maybe to have habitable conditions for life as we know it. That's the nearest star. In the observable universe, I don't think I mentioned this earlier, but in the part of the universe we have access to, and again, we have this built-in horizon. For all we know, the universe may be infinite. We can't see beyond a certain point. But in the observable universe, there are approximately 10,000 stars to every grain of sand on every beach on Earth. The Orion Nebula is a stellar nursery. We no longer look at star formation as this nice, orderly process. Within this region that is the diameter of about the distance between our sun and the next nearest star currently, there are hundreds of stars in this nebula. It's being lit up by some of those stars that are 10,000 times as bright as our sun, but there are a lot of lower luminosity stars in this cluster as well. And a lot of these little dark features you see as pull-out are roughly the size of our solar system. And this region was first observed in the mid-1990s. One of the pieces of evidence that we have that these new planetary systems are forming in the Orion Nebula. We have evidence from meteorite discoveries that probably we think that one of these massive supernova explosions occurred near our solar system as our solar system was formed. There are certain short-lived radioisotopes that must have been incorporated in our solar system early on. We think that if we ran the clock backwards 5 billion years or so, that this would be a picture very similar to the birthing region for our sun. But this is a wonderful example of how words like nature and nurture are now applied in the physical sciences as well as the biological sciences. Now we don't just have single systems forming. This isn't just about gravity. It's about radiation and light and heat from all these stars. It's about turbulence. What these stars and their systems become depends upon the way these different birthing star systems interact. It's like siblings at a dinner table. You know, they're competing for food. The one who gets to eat the most becomes the biggest. That's kind of like what's going on here. And this is a process that in science we would call stochastic. You can't predict the outcome precisely based on just knowing how things start off, because there's so much going on here as these stars and new planetary systems are forming. So just as interactions characterize scientific processes, they also characterize, how am I doing with the time, by the way? We've got 15 minutes. 15 minutes, okay. I'll speed things up, okay? Yeah, because I want to get to the end here. They also, this is a part of the talk I like to call From Renaissance Scholar to Citizen Scientist, because if y'all think science is cool, y'all can become involved in doing science with us, and you don't need to get a degree in science to do it, in any field of science. So first of all, let's start, we did a journey through space. We're going to do a really quick journey through time. Some of you have seen this before. It's called the cosmic calendar, where we put the 13.8 billion year history of the universe. We compress it to one calendar year, where 1 second is equal to 500 years. The last lecture was talking a little bit about writing. On this scale of things, well, first of all, on this scale of things, I don't want to go too fast. The sun and its planets, the sun is a third-generation star, forms 2/3 of the way through the cosmic year, starting with the Big Bang, 2nd of January 1st. Okay, the interesting things as far as human civilization go don't happen until minutes before midnight on December 31st. So the development of writing, beer in Mesopotamia, who'd have thunk, right? You know, beer, important part of the ancient world. By the time of Christ, 4 seconds before midnight, this is what the Earth's population looked like. Those little red dots just kind of identify population centers in the ancient world. There were only about 300 million people on Earth. Fast forward in time 1,000 years, and the Earth's population only increased by about 10 million people. Now we go to the beginning of modern science, the Renaissance. Leonardo da Vinci did everything. The smartest person in the world today can specialize in one particular aspect of one of these fields, but the day of the Renaissance scholar with broad knowledge across many, many disciplines is long since gone. There were still less than 500 million people on Earth in the time of Leonardo da Vinci. We skipped some things. The end of the last millennium, this is what the population centers of the Earth looked like when the population reached 6 billion. And this beautiful satellite image shows you why most people by the year 2040 or 2050 will never see the Milky Way in the night sky. In fact, the projections have it that most people on Earth won't see more than a few stars in the sky. So let's think about that when we think about smart environmental lighting and preserving our beautiful dark skies. Last tenth of a second, we've written this big history. Lot of gaps, okay? A lot of gaps. But human beings have actually sketched out the history of the universe just in the last couple of decades. Middle of the 1990s, boy, there are probably some people around here, there's certainly students that weren't even alive at this time. For the first time, we saw galaxies whose light comes to us from a couple of billion years after the beginning of the universe. We discovered stellar nurseries in all sorts of different places and star-forming regions in our galaxy. And we discovered the first exoplanet. An exoplanet is a planet that orbits another star. It is a planet, even though technically the definition of a planet is it orbits the sun. Over the last couple of decades, the rise in discoveries of exoplanets has been exponential. On the left, a curve drawn to the number of planets that we've discovered in general. The count is well over 3,000 at this point in time. On the right here, a curve drawn to indicate that the number of potentially habitable, by Earth standards, potentially habitable right now is defined as worlds where the temperature might be conducive to support water, which is critical to all life on Earth. So the discoveries have been exponential. No, don't start yet. No, I'm not ready for you. No, come on. All right. Based on the statistics of our discoveries, we now think that there could actually be more planets than stars in the observable universe. And there are 10 million quadrillion stars in the observable universe. What I'm going to show you now is a really cool visualization. It takes some of it gives you an idea of the diversity of some of these different systems. It's called the Kepler Orrery. It was put together by a University of Chicago exoplanet scientist, Dan Fabricki, who also happens to be a person of devout faith, a Christian. And he put together this wonderful visualization. In the upper left-hand corner, you're going to see a little toy model of the inner planets, Mercury, Venus, Earth, and Mars in our solar system. The only thing you see here are colored-in circles that depict relative sizes of planets, open circles that depict different kinds of orbits. Nothing is to scale. This is like the true marriage of art and science, just to impart some idea of the diversity of worlds. So I'm going to start this movie now. Note the counter in the upper right is in days. So these orbits, the planets really don't orbit like that. This is greatly sped up in time. Can we maybe get the volume up? Oh, gee. This device does not like me. artistic representations of atoms. These are huge planets that orbit so close to their stars on this scale, you can't really even distinguish the orbits. And look at these guys, closest together. I've been telling people about a system called TRAPPIST-1, which I like to refer to as Red Dwarf and the Seven Earths. TRAPPIST-1 is a red dwarf star that's orbited by 7 planets that are all Earth-sized, well within the distance between the Sun and Mercury in our solar system. This is a system where somebody, an observer on any one of these worlds, looking at all the other worlds, could see surface features. Those planets are so close together and have remained stable over a very long period of time. And now I'm going to have to rush on a little bit. So the upshot, the reason we've been able to make all these discoveries, the reason our rise in scientific knowledge is exponential, is because science is a community effort. The LIGO collaboration that discovered gravitational waves, these 3 guys got the Nobel Prize in physics last year for this. But this project is a collaboration across 80 countries, over 1,000 scientists, not to mention engineers, educators, technicians. I'm of the opinion that I think we need to start to rethink how we award prizes and Nobel Prizes, because this effort would not have been possible without a community, in fact, a global community of scientists working together on this project. So really quickly, at my workshop yesterday, I told people a little bit about, oh geez, I'm sorry. There's a website. Something over there just doesn't like me. So one of the cool things about being a scientist at a planetarium, we've worked together with the University of Oxford to develop a website called the Zooniverse, which is a repository for right now about 70 academic research projects that people around the world participate in. We have over 1.5 million people that participate in one or more. It's not just science. There are humanities projects. Think about large research projects that require combing through a lot of digitized information, be they images or maybe digitized records, ancient papers, ancient papyri, anything where we need a lot of human eyes to glean, to help us mine the data. People are really good at pattern recognition. We heard a little bit about that yesterday, I recall. People are good at pattern recognition in a way that computers aren't so good at doing. What's cool about this is these are projects that we need people around the world. I'm not talking 1,000 people here, I'm talking many thousands, million, over 1 million people who are every bit as good at pattern recognition as the people with the PhDs. On this website, you go to the Zooniverse, you'll see that there are all sorts of talk forums where people can collaborate with the scientists. They can learn about what these projects are all about, and they can participate, and they've made some incredible discoveries. And unfortunately, I want to get to some of these reflections, so I can't go through the discoveries that have been made. But suffice it to say that citizen scientists have won prestigious awards from the American Astronomical Society for their contributions, and have made it onto papers, peer-reviewed papers with scientists, based on the hours of time that they've committed to this and the discoveries, having made new discoveries. So, and again, I'm really sorry I have to rush through this part. So, some takeaways. The only constant is change, Heraclitus of Ephesus. Understandably, ancient peoples thought that this applied to the earth, but not to the universe as a whole, not to the skies, not to the heavens. Today, we see the cosmos itself as a product of change through the relationships and interactions of its parts. Galaxies and clusters of galaxies form and evolve under the influence of gravity, dark matter, and dark energy. Stars and planetary systems form through a delicate interplay of cosmic processes. Stars cook up the heavy elements needed for organic chemistry and life. Life that continually interacts with its environment has arisen on at least one planet, perhaps on more than we could possibly imagine. As small as we humans are in some sense capable of putting the cosmos into our heads. We are, in a very real sense, the universe becoming aware of itself. And a final note, we alone on Earth are the species that has the power to protect our environment, protect the delicate web of relationships that is life on our planet, and I sure hope we do. So finally, some reflections here. It's looking like, actually we're kind of going back in time in this sense, it's looking like the universe might be more productive to envision the universe as a giant evolving organism rather than a mechanism, an intricate network of relationships which we are a part, not apart from. The universe is fertile. It's brought forth incredible diversity, and there are some theologians that have written about this. Father George Coyne at the Vatican Observatory, Lutheran theologian Phil Hefner talks about humans as created co-creators. So one might think of the universe as both reflecting and participating in God's creativity. And here's where I love the language of Trinitarian theology, because the way we articulate our understanding of God is that this idea of relationship is fundamental to the way we talk about God, and of course relationship is also fundamental to love. And finally, J.B.S. Haldane, geneticist, evolutionary biologist, the universe is not only queerer than we suppose, it is queerer than we can suppose. So what does that tell us about God? It tells us not to put God in a box. So thank you very much. Oh gosh, all right. I know we don't have time for this. This is such a beautiful poem. I showed it at the end of my workshops yesterday, Christ in the Universe, written by a Roman Catholic suffragette, a mother of 8, in 1917, about 10 years before the first pulp science fiction about travel to another world. She writes this beautiful poem about the cosmic Christ, Christ in the universe, and comparing different gospels as we encounter other beings. So thank you I'd read it, but I'll start tearing up, and I'll also go way longer than my time permits. So thank you all very much.